Okay, take 3. Hopefully my phone doesn't cut me off this time again. All right. Whew, let's try to get back on track. Okay, we have the infinitely long list, right? That's the infinite series, has an infinite sum, S. We're going to approximate that infinite sum here by doing the fourth partial sum. So adding together these first 4 terms, that's our approximation for adding all infinitely many of those terms together. But of course, only using the first 4 is ignoring and neglecting everything starting from the 5th term and onwards, right? Remember, all those terms are called the tail. The summation of all of those terms in the tail, that's called your remainder or your error. And we want to know, like, what's the biggest possible size that this could be? What's the biggest error our approximation could have been? So let's investigate it. Think about this number to yourself, right? 1/5 would be 0.2. If I have this number by itself, 0.2, that's great. It's a pretty big sized error, but we'll see. If I get the next 2 terms, right? So if I, instead of having this by itself, if I have these 2 terms together, if you have your own calculator, you can calculate it. But if I do 1/5 minus 1/6, if I have one positive term and one negative term, the collection of those 2 terms together is going to be smaller than that first term was by itself. I know 100% of the time, every single time, that 0.2 minus something is going to be smaller than the 0.2 was by itself, right? So the first term, that 1/5, that first term in the tail, that by itself had a bigger size than the 2 terms added together. Let's look, if I were to do 3 terms, so I had the 0.2, I lost some, and then I gained some back, but 1/7 is smaller than 1/6. So you have the 0.2, you lose some, and you gain some back, but you're not going to gain enough back to get back to the 0.2, right? Like, having the 3 terms is going to be bigger than having the 2 terms, but it's not going to be the same as what that initial term was by itself. And then you would lose some more, and then you would gain a little bit back, and then you would lose some more, and you'd gain a little bit back, right? This list of numbers in the tail goes on forever. But even if you were to add all infinitely many of those terms together, that accumulation of all the terms in the tail is going to be smaller than the first term was by itself, because they alternate, right? And as soon as you start to have negative and positive stuff, it cancels out against itself, and then it's not going to be as big in size as the first term was, right? Hopefully that makes sense. This term is bigger than all of the terms in the tail added together, right? Because it alternates. Let's look at what happens, same series, but let's look at what happens. What if I do the 5th partial sum? Well, then my error would be all of the terms in the tail added together, starting with the 6th term. Again, the first term being negative, yeah, that means your error would be negative. That'll tell you whether you have an under or an over approximation. But really, we just want to know the size of the error, right? I don't really care about the plus or the minus. We're looking for the size of the number. The previous example, we had a positive, then we lost some, then we gained it back. Here we're going to start with the negative, but again, you're thinking about just the size of that number as opposed to whether it's plus or minus. The size of this number is 1/6, right? Negative, again, will tell you under or over estimate. You don't really care. The size of that first term in the tail is 1/6. If I were to get the 2 terms together, right? I have the negative 1/6 plus 1/7. If I were to add those 2 things together, one of them was negative and one of them positive, the size of those 2 terms combined would be smaller than this, right? Because you have negatives and positives, they would cancel out against each other, and it would be a smaller size than that first term was by itself. You would gain a little bit more of the negative stuff back, and then you would lose some with the positive, so on and so forth. So it doesn't matter if the first term in your tail is a positive or the first term is your tail in a negative. The idea will hold, and it'll be the same either way. The first term of your tail, its size is bigger than all of the terms in the tail combined. And that's the whole idea behind this alternating series error bound. That first unused term is the maximum error. It's the biggest mistake you could have possibly had made by omitting and not using any of those terms in the tail. All right, so it's a little bit weird conceptually, but actually doing questions with it, if I can pick up this piece of paper, actually doing questions with it are really not too bad. let's recap it. So in other words, if you have a convergent alternating series, you can approximate what that infinite sum is. Can't find it exactly, but you can approximate it by doing a partial sum. That partial sum has an error. The maximum error or the maximum remainder you could have had. All you need to do is look at the size of the first unused term or the size of the next term. Hopefully that makes sense. If not, it's not too hard to do it even if you don't understand it. So let us go through the couple of examples on this page, and then hopefully my phone doesn't cut out on me anymore, and hopefully we can be done. Okay, here we go. Example, given the series, approximate the sum by using the first 4 terms. This is going to be a calculator question. I don't have my calculator, but I have the answers already done, so that'll work. First thing you would want to check, is it going to converge? Well, yes. It's going to alternate in sign. That in factorial on the bottom is going to give you the limit of 0, so it is going to converge by the alternating series test. You would need to check to make sure it converges before you start talking about this alternating series error, but of course it's going to work. Otherwise, you would say, can't do the error. Okay. But here we go. Using the first 4 terms, let's approximate what that infinite sum would be. I think I've got that here, right? So that infinitely long list, not going to write it all out. Here I'm just going to do the first 4 terms, change the factorials, 2 factorials 2, so on and so forth. It looks like if I add those first 4 terms together, I'm going to get 5/8 or 0.625. That's great. That's not the exact value of the infinite sum, but it's an approximation. Part B, explain why the estimate found in A, this, differs from the actual value by less than 1 over 100. So what I want to do is look, right, this was my 4th partial sum. I want to see that the error, the maximum error that I could have had using the 4th partial sum is less than 1 over 100. So let's think about it. The error for the 4th partial sum is going to be smaller than the 5th term by itself, the 5th term individually, and that's the size of the 5th term. You don't care if it's plus or minus. So let's look at this, and this is how you should really write your work for this error-bound stuff. The error, and if you want to, you could write something like, let's see, it would be the error, so R of 4, the error or the remainder for the 4th partial sum, it would be less than the 5th term by itself. So you'd look at the next term in the list. Again, you don't care about the plus or the minus. The absolute value is going to kill it anyways. If I look at this next term, 5 factorial is 120. Since 120 is bigger than 100, I know this would be smaller than 1/100th. So the biggest error you could have possibly have had is this. And this is going to meet your required amount of accuracy. This is smaller than what the question asked for. Right, so it's going to work. The maximum error for the 4th partial sum would be the 5th term by itself. The 5th term is smaller. It differs by less than the 1 over 100. It differs by less than that value. So always try to make your work look like this, and then the answer, the AP graders, they're just going to say check, 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 because it'll look exactly like their answer key. But since my error is less than this, which is in turn less than this, the transitive property, you know your error, which again, you could write it like this. Your error is going to be less than 1 over 100. Okay, part C, use your results. Remember, I have my approximation, and now I have my max error. Let's use these results to explain why the infinite sum, that's the true exact value, S, of the infinite sum, why can't that sum be 0.7? Well, let's take the approximation, and let's use my max error, and let's take this approximation, we're going to add the max error to it, and then we're going to take my approximation and we're going to subtract the max error from it, and we're going to create this little window of possibilities where the true exact infinite summation could be. Take the approximation, add the max error, take the approximation, subtract the max error, and that's going to give you a little interval, this window of possibilities for where the real exact value could have been. Hopefully that makes sense. So here we go, my exact value, if I take my approximation and I add the max error, that's the biggest I could have been, right? If I take my approximation and I assume worst case scenario, if I assume I add in the max error, that's the biggest your infinite sum could be. Or on the other end, if I assume worst case scenario, but on the under approximation side, take my approximation, subtract the max error. Let's see, do all the calculations, this minus this plus this, it's going to give you this little interval of possibilities. And this tells you, hey, this infinite sum, I still don't know exactly what it's going to be, but it has to be something in between those two numbers. is 0.7 between those two numbers? Definitely not. So my exact sum cannot be 0.7 because 0.7 is not in my interval of possible values, right? Take your approximation, add the max error, take your approximation, subtract the max error, and then that's going to give you your little interval of values where that real exact solution could fall between. Okay, one more, and then we're done for this second lesson.